Hello students, this video is on end behavior of polynomials and recognizing even versus odd functions. Okay, we're going to start with end behavior of polynomials, and one thing that you just need to recognize when it's asking for the end behavior of the polynomials is it's asking for literally what's happening on the ends of the function. So if you're given a graph like this example right here, we're looking at the ends of the functions. So this end and this end. Okay, so one thing that, and there's a notation that we're going to use. So one thing you need to think about is, on each side, like, is it going to infinity or negative infinity? Well, when I'm looking at my x values, when they're on the right side, they're going to positive infinity. If I keep going to the left side, that's all my x values are going to be reaching negative infinity. Then on the y-axis, if I go up, then those y values are going to go towards infinity, and when my y-axis is going down, then that's going towards negative infinity. And so we're going to use this when we write our end behavior of our function. And so let me bring this in. This is the notation that you're going to see for end behavior, but it's not always written for you, so you need to be able to write it yourself. And so let me just kind of emphasize what you're going to do here. So what we're doing here is we're writing a statement, and this says, as x approaches negative infinity. So as my x values are approaching, negative infinity, then my f of x, which remember is your y values, your f of x is approaching what? Well, if I'm looking at this graph, as I'm following this graph and going to where x is going to be negative infinity, the left side, what is my y values doing, or what are my y values doing? Well, they're going down, and so they're going to eventually they're going to approach negative infinity. The next part of the statement is talking about the right side. As x approaches positive infinity, so as I'm going along this graph and I'm going towards the infinity side of x, so this side, what is my f of x doing? Well, my f of x, which are my y values, they're going up, and so they would be approaching positive infinity. So sometimes you're just filling in the end of this, and sometimes you're writing the whole statement. And so you want to keep in mind that as x approaches negative infinity, you need a left side, which is this, and then as x approaches positive infinity, that's the right side. So you need both of those, and then you're just filling in what the f of x is doing. Okay, so let's look at this example here. So they've given you the graph, and they want you to write the end behavior. Now, they've given you the beginning part. All they expect you to do is just fill in the end piece. Okay, so I want you to pause the video, and I want you to write down what you think needs to go at the end there, and then press play when you're ready to check it. Okay, so hopefully you got, as x approaches negative infinity, f of x is approaching negative infinity. And then as x approaches positive infinity, f of x is approaching negative infinity as well. Again, you're looking at as x approaches negative infinity, so that's going to be your left side. What's happening? It's going down, so I'm going to put a negative infinity. And then on the right side, as x approaches positive infinity, what's happening to my y values? They're going down, so I'm going to fill it in with a negative infinity. Okay, so now let's look at characteristics of polynomials when it's written in standard form. And so I want to do a little bit of a discovery here. When you have y equals x squared, of course, you can graph that by hand, but just to save time, we're going to graph it on Desmos. So when I have y equals x squared, this is what it looks like. Okay, now I want you to focus on what's happening on the ends. What's happening at the end behavior. So as x approaches negative infinity, the f of x is going to positive infinity as x is approaching positive infinity. F of x is approaching positive infinity. Both sides are going up. Okay, now let's compare that to x to the third. So I'm going to turn off the x squared. Oops. And I'm going to look at the y equals x cubed. Okay, well, hopefully you're noticing that, okay, the right side is still going up, but now the left side is going down. So they are going opposite directions. Okay, well, let's look at x to the fourth. X to the fourth looks very similar to x squared. It just has a little bit flatter base, but both ends are going up, right? Okay, well, what about y equals x to the fifth? That looks very similar to x to the third too, but it has a flatter, like, turning point. Okay, and so what I want you to notice is, notice that what could we say about x to the third, x to the fifth? When you look at those exponents, what do we notice about that? Well, hopefully you're noticing that both of the exponents are odd. So when it's odd, maybe it's always going to go in opposite directions. Well, we could test it out by typing in another odd function. So y equals, sorry, let me turn off my, sorry, I can't get the equal sign because this needs to move. Let me move it, make it just a little bit larger. So y equals, then I'd have x to the power of 7. Well, let's see. Oh, it looks very similar too, and it's going opposite directions. So I wonder if that's a trend. Well, it actually is a trend. Okay, well, let's compare the other one. So I'm going to turn off the y equals x to the 7th, turn off the y equals x to the 5th, turn off the x to the 3rd. Now let's look at the x squared. And let's compare that to the x to the 4th. Well, they look very similar, but notice about the end pieces. The end pieces are both going up. And so it looks like the end pieces would be going the same direction if we have an even exponent. So x to the, let's now do 6th power. Well, look, they're both going the same direction. And so anytime you have an even exponent, they're going to go in the same direction. Now, if I go back into these and put a negative at the front, remember the negative is just going to reflect it over the x-axis, right? So the only thing that it does is it's just going to reflect it, but what you want to notice is now, since I've got that negative leading coefficient, both sides are going to be going down. Well, let's see what happens when we look at the odd function. So when I turn on x to the 3rd, if I put a negative out front, that's going to flip the directions, but notice what's happening on the right side. The right side is going down. Right would go down, and then the left would go up. When I take the negative off, right, the right side was going up. So notice that when that leading coefficient was positive, whether it's even or odd, that right side's always going to go up. But as soon as I put the negative in, that right side is now going to go down, whether it's a positive or whether it's an even or an odd function. So if I look at x to the 5th, okay, turn off the x to the 3rd one. There's my x to the 5th. The right side is still going up, but as soon as I put a negative in front, it flips, and now the right side is going down. Okay, the same thing would happen with the x to the 7th. And so I just wanted to emphasize that, and so let's now look at an equation. All right, so from that discovery right there, I hope that you kind of realized what's happening. We can determine what's going to happen, what the end behavior of the polynomial is going to be based on the degree. Remember the degree. When I look at this degree, that means the highest exponent. So when you're looking at a standard form, you're trying to look at the highest exponent. So that's what degree means. The degree of the function is found by just looking at the highest exponent. And that highest exponent, if it's even, then the ends are going to go in the same direction. And if it's odd, the ends are going to go in the opposite direction. Okay? And that's all that. And then the degree also determines what happens on the left side. We'll talk about that in just a second. Okay, the LC, which I call the leading coefficient. Okay, so I just have abbreviated it, but LC just stands for leading coefficient. Well, the leading coefficient, if it was positive, remember that right side went up, and if it was negative, the right side went down. So you're going to start there. You're going to start and determine what the leading coefficient is telling you happens on the right side, and then you're going to look at the degree, because then the degree is going to tell you what happens on the left side. Okay, so when we have it in standard form, here's an equation, an example. We've got y equals 2x to the third minus 4x squared plus 5x to the sixth minus 8x to the seventh. Well, the first thing you need to do is you need to put it in descending order. So we've got y equals, the highest exponent would be that negative 8x to the seventh. Then next I would put plus 5x sixth. And then I would put a plus 2x to the third. And then I would have minus 4x squared. Again, we're trying to put it in descending order, which means our exponents need to be decreasing. Okay, so my leading term is that negative 8x to the seventh. All I need to look at is that leading term, because that leading term is going to give me my leading coefficient. Well, my leading coefficient in this case is negative, right? Because negative 8 is my coefficient. That would be a negative. Degree, now I'm looking at this guy right here, the exponent. So is 7 even or odd? Well, 7 is odd. And then now I can kind of see what's happening, right? The leading coefficient means my right side is going to go down because it was negative. And because it's odd, an odd degree, then the left side is now going to go in the opposite direction. So that must mean my left side is going up. Okay, so we can kind of see what this polynomial is going to look like. Now, sometimes they also ask you the number of turning points. Well, the number of turning points is always going to be the degree minus 1. So in this case, our degree was 7, and 7 minus 1 is 6, so it has 6 turning points. And then the number of possible zeros always matches your degree. Let's get a different color. It always matches your degree. So in this case, it has 7 zeros. Okay, so we can tell all this information really just by looking at that leading term. That leading term is going to tell us what the leading coefficient is, the degree, the number of turning points, and the zeros. Okay, now let's move into even, odd, or neither functions. When you're looking at a graph, you're going to be able to determine whether it is an even or an odd function because of its symmetry, okay? If it is symmetrical over the y-axis, in other words, if I cut it down the y-axis, is it the same on both sides of that y-axis? If it is, then it's going to be an even function, okay? Now, try not to focus on the fact that the end behaviors go up on both, because look, this one right here, the ends go up as well, but if I look at that graph, it is not symmetrical over the y-axis. So this one, even though the degree would be even, the function would not be even. Okay, Let's look at what happens when it's an odd function. When it's an odd function, it's going to be symmetrical around the origin. This is kind of hard to tell, but like if you were to put your pencil on that origin and you were to rotate your paper around that origin, then you could get the graph to turn into the exact same graph. So kind of, I can't really turn it on the video, but like if you visualize me holding this down and you turn the graph, if I turn it 180 degrees, it's going to be the exact same graph. So if it is symmetrical around the origin, then this is considered an odd function. Now again, don't focus on the end behaviors because I know the ends are going opposite directions, but in this graph right here, they're also going opposite directions. But if I was to put my pencil on that origin and rotate that graph, then it's not going to match up. It's going to be a different graph. And so that's how you tell when you're looking at a graph. Now, you can also tell whether a function is even, odd, or neither by looking at it algebraically. And they're going to ask you to prove this. And so what you want to look at is there's some rules here. If it's an even function, then if you do f of negative x, it's going to equal f of x. So, for example, if this is my f of x, if my f of x is this equation right here, and I substitute in negative x, so f of negative x would be me substituting in a negative x everywhere I see an x, and now let's simplify it. Well, negative x to the fourth power would be positive x to the fourth power. So this would be 2x to the fourth power. Negative x to the second power would be positive x to the second power, so minus 3x squared. And then the plus 5 does not change. Now I want you to compare these. If I compare what I got when I did f of negative x, and I compare it to f of x, are they the same? Well, yes, they are, right? So these are the same, therefore it's an even function. Okay? All right, well, let's look at the rule for odd. An odd function is that when you plug in negative x, so for your function f of negative x, it's going to be equal to the opposite of f of x. Okay, this is different. This, it's equal to the f of x, but when I plug in a negative x here, it's going to be the opposite of f of x, and that would be an odd. Okay, so let's try it. If this is my f of x, when I substitute in f of negative x, let's see what we get. So 3 times negative x to the third power minus 2 times negative x. When I simplify that, negative x to the third power is negative x to the third power times 3, so negative 3x to the third power. And then negative 2 times negative x is a positive 2x. Well, now we need to compare, okay? Well, my 3x to the third in the original function became negative 3x to the third. And my negative 2x in the original became positive 2x. So when I compare these, aren't they the opposite? And that's what needs to happen, right? When I plug in f of negative x, it needs to be the opposite of f of x. And so when they're all opposite, then it's going to be odd. Okay, let's look at this next one. So this one I'm telling you is neither. Okay, well, let's see why it's neither. Well, this is my f of x. But to compare, you always want to plug in negative x. So I'm going to do 2 times negative x to the third power minus 2 times negative x plus 3. And let's simplify it and see what we get. Well, negative x to the third power is negative x to the third power times 2 would be negative 2x to the third power Minus 2 times negative x is a positive 2x, and then plus 3. Okay, well, let's compare these. The first term in the original function was opposite when I plugged in negative x. Okay. The second one, negative 2x, also was opposite. So far it's looking like an odd function. But then in the original, I had a positive 3, and here it was the same. So what I'm looking at is I'm looking at opposite. Whoops, sorry, let me get my pen back. Here, the first term was opposite. The second term came out to be the opposite, but the third term came out to be the same. Well, if you have opposite and same, like it doesn't match the even or the odd rules. And so in this case, you have to say that it's neither. Okay, that's all I got for you on even and odd functions and in behavior. Go ahead and do your practice problems, and I will see you soon.